Hello everybody. This part is linear dependence and span, and it's from section 1.3 and 1.7, and two new terminologies will be introduced, span and linear independence. So let's start from definition. What is span? The set of all linear combinations generated by v1, v2, vp is span of these vectors. So back to the story of the Spider-Man, if he was taught a moving skill set, v1, v2, vp, then combining these moving directions, you can reach many points. And the collection of all those points Spider-Man can reach is the span of this moving skill. Now, we have following equivalent statements. So a vector y is linearly dependent to v1, v2, vp. This means this is equivalent to y is linear combinations of this set. Now we can, using the terminology span, we can say y belongs to or is in the collection of all those points, which is span. And the way we identify y is linear combination of this set or not is to see the augmented matrix by justifying its consistency. Now in the last lecture, we have seen one example with 5 vectors. So the moving skill sets are given by 3 vectors, v1, v2, v3 in the 3-dimensional space. And there are 2 villains, y and z. Last time we concluded that y is linear combination of v1, v2, v3, and z is not linear combination of v1, v2, v3. Then what does it mean? This actually means y is in span of v1, v2, v3, and z is not in the span of v1, v2, v3. In addition, we can actually figure out how many steps the Spider-Man should take to reach y for each direction v1, v2, v3 by solving augmented matrix. And the second question is actually to prove y is in the span of v1, v2, which means that Spider-Man can reach y only using v1, v2. He doesn't need v3 to get to y. Let's see how to figure this out. So for this second question, we should solve for that. So for the second question, we only want to use v1, v2 to reach y. Then is it possible? So what we do is we look at v1, v2, and y. And this time we want to solve for it. So when I write all the numbers, this is already in the shape of REF or REF. So basically, if we solve that, then x1 is basically 3, x2 is 2. What does it mean? That means because there's no free variable, this is unique solution. That means v2 y can be captured by using 3 steps of v1 and 2 steps of v2. In this slide, we are going to introduce linear dependency of a set of vectors. So first of all, you're given a set of vectors, v1, v2, all the way up to vp. And we call this set as linearly independent if the following homogeneous vector equation, x1 v1 plus all the way up to xp vp equals 0, has only one solution, which is trivial solution. If we look at this homogeneous equation, we call this equation as homogeneous because the right-hand side is 0. This is very special. If you have vector equation on the right-hand side 0, then it must be consistent. In other words, at least one solution exists. And the first solution you can think of is 0 solution, which is called trivial solution. So there's no way it can be inconsistent. Now, our linear independence requires there's only one unique solution. In other words, there's no more solution other than trivial solutions. What if there's other solutions, non-trivial solutions? Then we call that linearly dependent. Well, we're going to use some examples to understand this concept and try to visualize this into n-dimensional geometry. But first of all, we need to know how to identify a set being linearly independent or not. So if we look at this vector equation, first of all, this is linear system, and it's equivalent to solve augmented matrix written by this. This is augmented matrix. Well, when does it have unique solution? This is equivalent to ask when is the set linearly independent. So this augmented matrix has unique solution if and only if there's no free variable. There's no free variable. All right, that gives me the next slide. So this is rule, how to identify a given set is linearly independent or not. A vector set is called linearly independent if and only if this augmented matrix has no free variables. This is the way how to identify linear independence or not. Next, we're going to look at one example. First, we want to prove that a set of vectors v1, v2, v3 is dependent. Those 3 vectors are given here. We've mentioned earlier, which were considered as a moving skill set for a Spider-Man. Now, we want to prove that v3 is actually redundant in a sense that span of v1, v2, v3 equals span of v1, v2. What does it mean? So the Spider-Man has a set of moving skills, 3 vectors in his moving skills. Now, using combination of these three vectors, he can move to many, many points, which is span. The collection of all the points he can reach is span. Span, which means Spider-Man can reach. Now, V3 is redundant means here. So, or span of V1, V2, 3 equals span of V1, V2. What does it mean? It means actually Spider-Man using combination of first two scales can reach anywhere he can reach by using combination of three scales. So number 3 vector is not really useful in terms of this sense. So to prove that, there's a hint. You need to prove V3 can be reached by V1, V2. Or you can say V3 is a linear combination of V1, V2. All right. So we first want to prove V1, V2, V3. They're linearly dependent. So to prove that, first we look at their augmented matrix, V1, V2, V3, and 0. And it can be written as 1, 0, 0, 0, 1, 0, 1, 1, 0, and 0, 0, 0 other side. And then this is immediately a form of RREF, and we find that this is free variable. So if there is free variable, then that means this has more than one solution. And if there are many solutions, then we can say they are linearly dependent set. Now, second one is asking for span of V1, V2, V3 equals span of V1, V2. So it's enough to show V3 is linear combination of V1, V2. To do that, we should look at following augmented matrix, V1, V2, using these two moving scales. Try to reach V3 position. Then this augmented matrix is 1, 0, 0, 0, 1, 0, but here is the bar separating right and left hand side. So V3 becomes answer column. And this is RREF. What does it mean? There's no free variable. And the last column is also not pivot. In other words, there exists unique solution. The solution is x1 equals 1, x2 equals 1. So these two numbers give the weights of V1, V2. In other words, V3 can be reached by using one step of V1 and one step of V2. And because no free variable, this is unique solution. All right, next, we're going to see one statement. The statement says, if Y is a linear combination of V1, V2, Vp, then the set V1, V2, Vp together with Y is dependent. We're going to prove this directly from the definition. So what do you mean by Y is a linear combination of these P vectors? That means because Y is in the span of V1, Vp, we can write y can be reached by x1 v1 and xp vp for some non-zero step size. Now if I move this around and make 0 one side, then that means we come up with the following expression. So I will move y to the other side and make 0 on the one side. What does it mean? It means for the set v1, v2, vp, and y, you have non-zero coefficient x1, xp, and negative 1. To make it 0, this is exactly the definition of dependency. So because non-zero set makes those coefficient, makes the 0 vector equation, so v1, vp, and together to y is dependent set. So we can say y, if y is linearly dependent to v1, v2, vp, then the set having v1, v2, vp together with y must be dependent. So this is the same as y is linearly dependent to y v1, vp, then you can say the same thing. All right, the next one is a little bit tricky. So it's a question, it's not a statement. If y is not linearly dependent to y, v1, v2, vp, then can you say the set v1, v2, vp together to y independent? The answer is no. So we can again look at the set given here. And I'm going to put it here. All right. So here we can see that z, we have proved that z is not in span of v1, v2, v3. However, we have seen that v1, v2, v3, and if you put the z together, then is dependent. Why? Because v3 equals v1 plus v2, which was derived here. v3 is v1 plus v2. And then you can write it as v1 plus v2 minus v3 plus 0 times z equals 0. So this means v1, v2, v3, z is dependent set. Thanks for watching.